Welcome back to my channel. This is part 2 of our Introduction to Calculus series, and today we're exploring logarithms. Let's get started. What's the opposite of exponentiation? Some would probably say it's the square root. In fact, that's what many schools teach. See the logic behind it. 3 raised to 2 is 9. The square root of 9 is 3. 4 raised to 2 is 16. The square root of 16 is 4. And you can make the same thing for the cubic root. 2 raised to 3 is 8. The cubic root of 8 is 2. The same applies to any root. So we conclude that the opposite of exponentiation is the root function. Right? Wrong. As you have seen in the previous video, the function root is a special case when the exponent is a fraction. This happens because both share the same propriety. They return the base when multiplied by itself. So, what is the inverse of a power? It's a function called logarithm. An exponent shows how many times a number is multiplied by itself. For example, 2 raised to 3 is 2 multiplied by itself 3 times, which is 8. A logarithm works in the other way. It asks, what exponent gives this result? A logarithm tells us how many times one number must be multiplied to get another. Therefore, the answer to a logarithm is the exponent. In this case, the logarithm of 8 to base 2 is 3, the exponent in our previous example. Always remember, when you are calculating a logarithm, you are searching for an exponent that gives this result. Try this one. What is the logarithm of 1 to base 2? We are looking for the exponent with base 2 that gives 1 as the result. Think for a moment. What is the exponent that always gives 1 no matter the base? 0, right? That gives us our first rule. The logarithm of 1 is 0, regardless of the base. Another easy one. What's the logarithm of 2 to base 2? In other words, what exponent gives the same result as the base? 1. And that gives us another rule. The logarithm of a number that's the same as the base is always 1. Let's make it a bit harder. What's the logarithm of an exponential number with the same base? It sounds tricky, but think about the definitions of logarithm and exponentiation. Replace the power with y. And what do we get? A, the exponent. We can use the same method to calculate a number, raised to a logarithm with the same base. In this case, replace the logarithm with a. And that gives us y. Let's use this last rule to make this calculation. We can replace m and n by the base raised to the logarithm with the same base. Remember this rule of exponents? This means we can add the logarithms since we have the same base. Now, let's consider this rule. And what we have? The exponent. This is a very powerful rule because it turns multiplication into addition. But we can also turn division into subtraction when using this rule of exponents. And if we consider logarithm of 1 as 0, then we have one more rule. Consider multiplying the same number a times. This is the same as raising the number to the power a. Thus, we can conclude that it's the same as adding the log of m a times. Or, in short, multiplying the log by a. Don't mix up this rule with this one. In this, the number is the same as the base. Here, they're totally different. But if you look more closely, you'll see the second rule is, in fact, a special case of this first, where the number m is the same as the base x. And since the log of a number with the same base is 1, you're just left with the exponent. Now, Think about this logarithm. We want to calculate this exponent, right? The solution is simple. 2. The same applies to these logarithms. This means we have to multiply 10, 2, 3, 4, and 5 times. However, it's not that easy when you want to calculate this logarithm. Fortunately, most calculators, including what you have in your computer, have a key to this logarithm, which is called the common logarithm, usually written as log of x. It tells how many times we should multiply the base 10. In this case, the result is between 2 and 3. So, we know we have to multiply 10, 2 times and little something more. Take another look at your calculator. You'll see a button near the log that says ln. That's for another special logarithm, so special that mathematicians call it the natural logarithm. And it's written as ln x. Its base is the Euler number, represented by the letter e. Think about pi. As you probably remember, it's a mathematical constant often rounded to 3.14. But it's actually an irrational number, meaning its decimal goes on forever without repeating. The same goes to the Euler number. It can be rounded, in this case to 2.72, but its decimal also goes on forever. I will talk more about this number in future videos, but for now, just think like this. Instead of writing out that huge number as the base, we'll just use the letter e. Let's plot the natural logarithm, considering it as function f of x. As you can see, it passes through coordinates 1, 0, and e1. If we plot another logarithm, let's say the common log, we can see that it passes through 1, 0, and 10, 1. In fact, all logarithms have this type of curve, called the logarithmic curve, and pass through coordinates 1, 0, and base 1. But let's go back to the natural log and try to find its counterpart. In fact, it's easy when you consider the definition of logarithm. This power is called, naturally, the natural exponential. Let's plot it. In this case, the graph passes through 0, 1, and 1e. Now, compare it with the graph of the natural log. It passes through 1, 0, and e1. And, if you look closer, you can see that the curves are similar. They're only flipped, proving again that these functions are the inverse of each other. As you've probably guessed, you should use the natural log or common log whenever you can. Not only are both on your calculator, but as you will see in my upcoming videos, using the natural log can help simplify math expressions. But what should you do when you run into a situation like this? In this case, you should use our last rule, which can be adapted to the natural log. Let's calculate our example. First, we use the natural log of the number and the natural log of the base. Then, we use the calculator to find both values and divide one by the other to get the result. But how to prove this rule? Consider n as the log base 2 of 50. According to the definition of logarithm, the exponent of 50 is 2 raised to n. Apply the natural log in both sides of the expression. You can use this rule in the left side to get the power n. Put ln2 in the other side. What is n? Our logarithm, thus proving our rule. Another version of this rule is when you use the same base as the number. In this case, the numerator is 1. This is very useful when calculating inverse fractions, like this one. All you have to do is to switch the number by the base and calculate a log you know the result. And that concludes our lesson about logarithms. If you've learned something new today, don't forget to like the video and subscribe. I'll see you in the next lesson.